Okay, so today's lesson is going to be on freefall, which, as we're going to find out, is just a special type of uniform accelerated motion. So let's first define freefall. So it's any object that moves through the air under the influence of gravity. Okay, only, so nothing else. So no wings, no engine, etc. So near the surface of the Earth, if we ignore air resistance, or we say that it has a very small effect, all objects, big or small, so large mass or small mass, accelerate at the same rate. So we call this the acceleration due to gravity. And we give it the symbol g when we're talking about an acceleration due to gravity. And on the surface of the Earth is 9.8 meters per second, or meters per second squared. So let's say we slip and fall, and we want to know how fast you're moving when you hit the pavement. So if we sketch a little picture of the situation, and we say that if we're going to fall, and we're going to fall on our derriere, and we're 1 meter above the ground, then we can say that we start off with a velocity of 0. We accelerate at a rate of g, which is 9.8 meters per second squared, and we know that we move through a displacement of 1 meter. We want to know how fast we'll be moving, so we want to know what is that final speed. So we have a v, we have an a, we have a v naught, and we have a displacement. So we don't have any time. So we have a v squared equals v naught squared plus 2a times the change in position. The initial velocity is 0. We're trying to get v by itself, so we square root this side, and we can square root that side, and we get v equal to the radical of 2 times the acceleration times the displacement of 1 meter. And if you do that in your calculator, you get a final speed of 4.4 meters per second. So if we're looking at an object, and let's say we toss a ball up and we watch it go up every second, so these dots represent its motion on the way up. So at the start, there it is, 1 second later, 2 seconds, 3 seconds, etc., and then it comes back down. Okay, so important facts based on the symmetry of the trajectory, that whatever speed it leaves with, because it's going to slow down at the same rate that it speeds up, that the initial speed that I throw it with is going to be equal to the speed it lands with. And likewise, the position that it moves through, the displacement that it moves through on the way up, is going to be equal to the displacement that it moves through on the way down. And likewise, because it's in the upward direction on the way up, and it's in the downward direction on the way down, since it's turning around, it must stop before it turns around. So the velocity at the top has got to be equal to 0. Okay, and we're going to apply these concepts in equations in a little bit. So let's talk about if we do have a significant air resistance. So if it is significant and it reaches a point where it's actually going to make a difference, we say that they actually fall with a constant speed. And there's a special term that we use for this, is terminal velocity. And we give it the symbol v sub t for terminal velocity. So to give you some examples, skydivers. The terminal velocity of a skydiver is about 120 miles per hour. Precipitation, so our rain, is about 10 miles per hour. And hail, maybe even upwards to 20 miles per hour. But what's really important is for this class is we're going to assume that air resistance is negligible, meaning that it has no influence. Okay, so since our bodies can sense, so if you were driving in a car and you had a blindfold, you were in the passenger of a car and you had a blindfold on, you would be able to feel the accelerations. Okay, so we typically report that number, the amount of accelerations, in a unit called G's, where the number of G's, to figure out the number of the G's, you take the acceleration and you divide it by the Earth's acceleration of 9.8 meters per second squared. So you take the acceleration in meters per second squared and divide it. So you get a number of G's. So to give you an idea that 1 G is normal. Right now you are experiencing 1 G worth of acceleration. Now 2 to 3 G's, that is a thrill. 4 to 5 would cause nauseous. You would feel nauseous or dizzy. 7 G's, you're likely to pass out. And greater than 30 G's, and especially for a long period of time, that can cause death. So let's take a look at a practice problem. A squirrel jumps out of a branch of a tall oak and falls 2.5 meters before it gracefully lands on the ground. How much time was it in the air? So if I list my given information, if it jumps out, it's got zero initial velocity. It's got an acceleration that is equal to g, which is 9.8 meters per second squared, and it falls through a displacement of 2.5 meters. If I'm asked to find how much time, t is my unknown, and now I'm going to find an equation that relates what I know to what I'm trying to find out. So if I use the delta x is equal to v naught t plus 1/2 a t squared, my initial velocity is 0, and if I do a little algebra to solve for t, I'm going to multiply both sides by 2. That cancels out the 1/2, and then divide by a. So I get t squared is equal to 2 times my displacement divided by my acceleration. And finally I can square root it, so I get a time that's equal to the square root of 2 times my displacement of 2.5 meters divided by the acceleration of 9.8 meters per second squared. And that gives me a fall time of 0.71 seconds. Now if I want to know how fast the squirrel's going just before it hits the ground, that I'm looking for my final velocity, and I can then just use, once I know how long, I can multiply that by the time in order to, or I can multiply that by the acceleration in order to figure out how fast. My initial velocity is still 0, so this is 9.8 meters per second squared times my 0.71 seconds. And that gives me a speed of 7 meters per second. Another example is if I toss a ball in the air. Now and I want to know how long it will be in the air. But remember, the final speed just before it hits the ground is equal to the initial speed. So if I throw it up with a speed, and now the velocity is, I'm going to call this a positive 8.5 meters per second. My final speed is going to be the same amount, but in the opposite direction, so it's going to be a negative 8.5 meters per second. Now, my acceleration is going to be g, But if I'm throwing it up positive, the acceleration is always in the downward direction, so it will be a negative 9.8 meters per second squared, and I want to know how long it's in the air. So t is my unknown. So relating what I know to what I'm trying to find out, I have v equals v naught plus at. Now I'm looking for time. So I'm going to subtract my v naught and then divide by a to get my time. So this is a negative 8.5 subtract a positive 8.5 divided by 9.8. That gets me a time of 1.73 seconds. And that's the total time in the air. Now if I wanted to find out how long it takes to get to the top, I could just cut that in half. If I want to know the maximum height, well, I know the speed at the top is 0. It's got to momentarily stop at the top. So in order to figure out that maximum height, I could use the time, okay, but I actually don't need to, because I know how fast it's going in the beginning, I know the acceleration, and I know the speed at the top. So I could actually use the timeless equation, v squared equals v naught squared plus 2a times my change in height. At the top, it's 0, so that is gone. I subtract the v naught squared, equaling 2a times delta x. I could divide by 2a, and I get my delta x to be the negative of v naught squared divided by 2a. So that gives me my height to be the negative of 8.5 squared divided by 2 times negative 9.8. So I get a positive displacement, which, because I get a negative divided by a negative, which makes sense because it's on its way up, and we called up to be positive. So I get 8.5 squared divided by 2 times negative 9.81. I get 3.7 meters. And that would be the maximum height. So it goes up 3.75 meters and then comes back down 3.75 meters. And in doing that, it takes 1.73 seconds to complete. What will it be its acceleration? Well, the acceleration is always equal to the negative 9.8 meters per second squared. And if you think that the acceleration should be 0 at the top, think about this. If I throw something up and it stops momentarily, and momentarily has an acceleration of 0, well, it would actually just stay up there. So the fact that it comes back down, it changes its speed from 0 meters per second to 0.1 meters per second, is the fact that it continues to accelerate. This is a constant value on the surface of the Earth. It never changes from that. So try out what you think that the acceleration time graph would be for this next example, and tomorrow in class we'll share our ideas. All right, so that's all for now. Thank you. Have a good night. Bye-bye.